Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is the 14th lecture. In this lecture, we will be looking at logic optimization. In the earlier lectures, we had seen that the logic synthesis task can be broken down into various simpler tasks as shown in this figure. In the last two lectures, we had seen RTL synthesis, and in this lecture, we will be looking into logic optimization. Logic optimization basically transforms a given netlist, which is in the form of generic logic gates, into an optimized netlist such that the functionality is preserved while its figures of merit, primarily the area, improves. Now, if we look into the logic optimization task, it is of two types. The first type of logic optimization is combinational logic optimization, which targets the combinational logic cones in a given circuit. And the second part of logic optimization is related to sequential logic optimization, or the finite state machine FSM representation of a given netlist. Now, the combinational logic optimization are of two types: two-level logic optimization and multi-level logic optimization. Now, these two types of optimization differ in the representation of a Boolean function. Now, in two-level logic optimization works on the representation of a Boolean function, in which the Boolean function is represented in two levels of logic as shown in this figure. It can be either sum of product form, right. So, we have all the products and then we are taking the sum of it. So, it is a sum of product representation, or it can be product of sum, right. So, it is the sum and we are taking the product, or it is a product of sum form, right. So, in this type, or in this representation, in these representations, there are two levels of logic, and followed by or followed by and. Only two levels of logic are involved, and the logic optimization which works on this form of representation is known as two-level logic optimization. And the other form of logic function, or another form of representation of the logic function, is multi-level form, as it is shown here. Okay. So, this is a multi-level logic representation, in which from the input to the output there are multiple levels of logic. In this case, there are 1, 2, 3 and 4 levels of logic involved, right. So, logic optimization which works on multi levels of logic, those are known as multi-level logic optimization. So, in this lecture we will be looking into two-level combinational logic optimization, and in subsequent lectures we will be looking into the multi-level logic optimization and also the sequential logic optimization. Now, before going deeper into the logic optimization, let us look into a statement from R.W. Emerson. The statement is, we ascribe beauty to which is simple, which has no superfluous parts, which exactly answers its end. Now, this statement was made in a different context, but it is very much relevant to logic optimization, because logic optimization basically tries to achieve this. So, what does logic optimization do? It tries to get rid of the superfluous parts of logic, right. As a result of that, our logic becomes simple, and also it becomes beautiful in terms of figures of merit. So, now let us look into that how logic optimization is able to achieve this kind of simplification and improve the figures of merit of our design. Before looking into two-level logic optimization, we should be familiar with some important definitions related to Boolean functions and logic optimization. Now, what is a Boolean variable? A variable that can take one of the two values 0 or 1, those are known as Boolean variable, and we represent Boolean variable by symbols like say x1, x2, a, b and so on. Now, what is a Boolean function? A function that takes Boolean variables as arguments and evaluates to 0 or 1. Those are known as Boolean functions, and we represent Boolean functions as y is equal to f x1, x2, x3 to xn, where x1, x2, x3, xn are Boolean variables, right. So, we call the y as the output of this Boolean function, and the Boolean variables on which this output depends x1, x2, x3 to xn, these as the input to the Boolean function. Now, what is a literal? Literal is a Boolean variable or its complement. So, it includes both a Boolean variable and its complement. For example, we say that if x1 is a Boolean variable, then x1 is also a literal, x2 is also a literal, right. Additionally, if we take the complement of x1, x1 dash, right. So, when we say that x1 is a variable and we write x1 dash, then x1 dash represents the complement of x1, right. So, x1 dash is also a literal, x3 dash is also the literal, meaning that any variable or its complement, both of them are considered as literal. Now, what is a cube? Cube is a product of literals, right. Product meaning the AND operation, where if we do AND operation of various literals, we get a cube. For example, x1, x2, x3 is a cube, right. So, x1, x2, x3 is basically x1 dot x2 dot x3, where dot represent the AND operation, and in short form we write as x1, x2, x3, and it is a cube, right. x1, x2, x3 is a cube. Similarly, x1, x2 dash is a cube, right. This is a cube, and also the literals are also considered as a cube. For example, x3 dash is also a cube consisting of only one literal, right. Now, let us consider a Boolean function of n variables, where n is a number, right, n is a number. So, now the if for a Boolean function of n variable, we can define a minterm. Now, what is a minterm? Minterm is the cube of n literals in which each variable or its complement appears exactly once, right. So, if a function is of n variables, then all the n variables should appear either as a variable or its complemented form, all of them should appear, and in minterm we have a cube, meaning that it is a product of the literals, right. Now, similarly, instead of the product or instead of AND operation, if we take the sum of n literals, we take the sum of n literals for a Boolean function of n variables, then we get a max term, right. So, again in max term, all the n variables should appear either as a variable or its complemented form, right. Let us take an example to understand this. So, consider a function of 3 variables x1, x2, x3, these are 3 variables. Then what could be the minterms? A minterm, an example of minterm is x1, x2, x3, right. Why it is a minterm? Because all 3 variables are appearing exactly once. Similarly, x1 dash, x2, x3 is again a minterm, because x1 is appearing as a complement form, but it is appearing, right, and x2 and x3 are also appearing. Similarly, x1 dash, x2 dash, x3 is also a minterm. But is x1, x2 a minterm? No, it is not a minterm. Why it is not a minterm? Because if you are considering 3 variables x1, x2, x3, x3 is not appearing in it, right, and therefore x3, x2, x1, x2 is not a minterm. Is x1, x2, x3, x3 complement, is it a minterm? No, it is not a minterm because the x3 is appearing twice. Each variable or it should be appearing as a literal only once. It cannot or exactly once. It cannot appear less than or more than once. So, therefore, this is also not a minterm. Similarly, max term are x1 plus x2 plus x3 because all the variables are appearing exactly once. x1 plus x2 dash plus x3 is another max term, right. Now, let us look at a few representations of a Boolean function. Why we should be worried about representation of a Boolean function? Because many logic optimization tasks and manipulation of Boolean function is strongly dependent on the representation of the Boolean function. For some Boolean function representation, the task may be very difficult manipulating them. For some logic optimization task or doing some transformation of a Boolean function may be much easier in some or in a given Boolean representation and may be very difficult in other kind of representation, right. And therefore, while doing logic optimization, the representation of a Boolean function is very important. Now, let us look at a Boolean function representation which is known as truth table. You might be aware of this from your course on digital circuits. So, the row in a truth table we have various rows, right, and in each row what it represents? It represents the value either 0 or 1 assigned to each input variable x1, x2, xn in a Boolean function and the corresponding output value, right. And since if there are n Boolean variable in a function and each Boolean variable can take a value 0 or 1. So, the number of possible combination of input variables is 2 to the power n, and therefore, the number of rows in a truth table will always be 2 to the power n, right. Now, let us take an example of a Boolean function y is equal to x1 x2 plus x2 x3 plus x3 x1 and draw its truth table, right. So, we have, since there are 3 variables here x1, x2 and x3, and we will have 8 rows. 2 to the power 3 is equal to 8 and therefore, we have 8 rows in the truth table, right. Now, each row represent assignment of the variables or each unique way of assigning variables in. So, if we take the first row, in this row we have x1 is equal to 0, x2 is equal to 0, x3 is equal to 0. Now, if we put x1, x2, x3 is equal to 0, 0, 0, then y will evaluate to 0 because all these terms will be 0, right, and therefore, y is equal to 0. Now, let us take another row. In this row x1 is equal to 0 and x2 is equal to 1 and x3 is equal to 1, right. Now, if we see y, x1, x2 will be 0, right, because x1 is 0, x2, x3 will be 1 because x1, x2 and x3 both are 1 and x3, x1 will again be 0, and if we take the sum of them we will get 1. Similarly, all the rows of the truth table are constructed, right. Now, let us look at another representation of a Boolean function which is known as minterm representation. Now, corresponding to each row in the truth table, we can associate a minterm with it, right. For example, so how do we construct the minterm for a given row of truth table, right? We construct the, for example, let us consider this row. So, for this row, for any row, what we do is that we construct the minterm by taking an uncomplemented value of the variable if it takes a value 1 and its complemented value if it is taking 0, right. So, x1 is taking a value of 1. So, we take it as not complemented x1 simply x1. Now, x2 is taking a value of 0 and therefore, we make it as x2 bar, right, and we take a complement of it or x2 dash, right, and x3 is taking a value of 1. So, we are not taking the complement, right. Similarly, we can associate or we can associate min term with each row of the truth table. Now, what will be the property of these min terms? So, the min term will be evaluating to 1 only for the assignment of variable corresponding to the row corresponding to that row in the truth table. For example, if we take this particular min term, it will evaluate to 1 if x1 is equal to 1, right, into x2 is equal to 0, right, and if we take complement of x2 dash, it will become again 1 and x3 is equal to 1. So, product of 1 dot 1 dot 1 is equal to 1. So, the min term will evaluate to 1 for the corresponding rows if the values of the variables are corresponding to that row, right, and for all other assignments of variable, the min term will evaluate to 0. For example, if we evaluate x1, x2 dash, x3 for any other row, we will see that one of these three terms or 3 literals will turn out to be 0 in the min term and therefore, this will turn out to be 0, right. So, what it means is that the min term will evaluate to 1 for only one row in the truth table or that the row corresponding to the truth table for which that min term was constructed. For all other rows, it will evaluate to 0. Now, using this observation, we can represent a function as sum of min terms. What we do is that we take the sum of only those min terms for which the function evaluates to 1, right. Now, in this case, the function evaluates to 1 for this case, this case, this case and this. So, corresponding to these min terms or the min terms corresponding to these rows, we take it and form a sum, right. Now, if we write y is equal to sum of these min terms, then this y will evaluate to 1, one of these terms will evaluate to 1 for each of these 4 rows, right, and for all other rows all these min terms will evaluate to 0 and therefore, y will evaluate to 0, right, and for these 4 rows one of these min terms, one of the min terms out of these 4 min terms will evaluate to 1 and therefore, y will take the value of 1, right. So, now we can represent a Boolean function, in sum of min term form, right. Now, let us look into another form of representation of a Boolean function, which is known as hypercube representation. Why we want to represent Boolean function in a form of hypercube? Because many of the logic optimization tasks that we will be looking for later in this lecture, those can be visualized very well on a hypercube, right, and therefore, let us represent Boolean function in terms of hypercube. Now, Boolean functions of n variables y is equal to f x1, x2, x3 to xn spans n dimensional Boolean space, right, and an n dimensional Boolean space can be represented and visualized using n dimensional Boolean hypercube, right. So, let us see what is an n dimensional Boolean hypercube. Let us take n is equal to 3, because for 3 dimensional hypercube we can easily visualize, right. Now, this is an example of this figure is an example of 3 dimensional Boolean hypercube, right, and we can associate each variable with one dimension of the hypercube, right. So, if we consider a Boolean function of 3 variables y is equal to f x1, x2, x3, these are 3 input variables x1, x2, x3, then we can associate one variable with, or we can associate each variable with one dimension of the hypercube. Okay. So, we say that in this direction is x1, in this direction it is x2, and in this direction we have x3, right. So, we can associate each direction, or we can associate a Boolean variable with each direction in the Boolean hypercube, right. And then the corners of the hypercube represent binary valued n dimensional vectors, right. Now, in the truth table we saw that each row represented the combination of values for the input variables, right. Now, in the case of Boolean hypercube, each corner represents the value assigned to each of the Boolean variable, right. So, for example, let us take this corner 1 1 1 0. So, the ith entry in the vector corresponds to the value of the variable xi. So, if we consider the vector as 1 1 0 for this corner, then we can associate this one or this first one with x1, second one with x2 and third one with x3, right. So, this point corresponds to the assignment of variable x1, x2, x3 as 1 1 0, where x1 is assigned to first one, x2 to the second and x3 to the third one. And we can see that if we take this variable, then at this point on the x1 side it is 1, right, on the x2 side it is 1, right, and on the x3 side it is 0, right. And that is why we can understand that the coordinate of this point, of this corner is 1 1 0, and we can understand that at the point 1 1 0, the value of x1 is 1, x2 is equal to 1 and x3 is equal to 0. Now, a Boolean hypercube has 2 to the power n corners, right. Now, if there are n variables and each variable can take a value of 0 or 1, we will have 2 to the power n corners. In this case, there are 3 variables and therefore, we have 8 corners, right. So, it represents 2 to the power n input combinations similar to a truth table, right. It is a representation, similar representation as a truth table. Only difference is that rather than writing it in a table form, we are drawing it in a kind of a cube form. Why we are drawing it in a form of cube? Because it will help us visualize the operations logic minimization task that we will be looking at subsequently in this lecture. So, we can also associate each corner with a minterm similar to what we had done for the truth table. For example, at this corner x1 is equal for this corner x1 is equal to 0, x2 is equal to 0 and x3 is equal to 0, right. And since all of them are 0, we can say x1 bar, x1 dash, x2 dash and x3 dash. This is the minterm associated with this particular corner. Similarly, if we look into this corner, right. So, x1 is taking a value of 0. So, we can take x1 bar, x2 and x3 are 1. So, we just write x2, x3 and this is the minterm associated with this corner, or in this case this corner, right, x1 dash, x2, x3, right. So, this we can associate each corner with one minterm. Now, how do we represent a Boolean function in a hypercube, right? So, we mark the corners in the Boolean hypercube with the value of the function for the associated input combination. So, in truth table we marked the value in a separate column, right, the output column, right. In this case, what we do is that we mark the value directly at the corners. For example, if we consider this function y is equal to x1 dash, x2 dash, x3 dash plus x1 dash, x2, x3 plus x1, x2, x3. So, there are 3 minterms, right, and if we draw the representation of this Boolean function in the hypercube notation, then we will just say that for this minterm which is correspond to this, we write 1. For this min term, right, this corresponds to the corner x 1 is equal to 0, x 2 is equal to 1 and x 3 is equal to 1, right. So, we say that 0 1 1, that is for this corner we write a value of 1. Similarly, x 1 x 2 x 3 correspond to 1 1 1 and we have 1. For other values for other corners we write a value of 0. So, this way we can represent any given Boolean function in a hypercube notation. Now, in some Boolean functions there can be do not care conditions. And what are do not care conditions? For some input combinations, the function y is equal to f x 1 x 2 x 3 to x 1 x n may not be specified, right. We do not know the values for those cases, or we are not given that values for those cases. So, these input combinations are known as do not care, meaning that in that case the value of y is not specified and it can be taking any value, it is 0 or 1. It is not, we do not care for those input combinations. So, we denote these DC do not care conditions as x, right. As we say that for 0 we write 0, for 1 we write 1, similarly for do not care we say x. Now, do not care conditions are related to the input combinations that can never occur in a circuit. Now, how can it be? For example, suppose we have we are designing considering a logic cone, combinational logic cone, in which the inputs are coming in a form of binary coded decimal, right. Now, binary coded decimal digits can decimal representation is in the 4 binary digits, right. So, it is represented in 4 bits, right, and the values that this binary coded decimal can take is between 0 and 9 and it is coded between 0 0 0 0 to 1 0 0 1, right. So, the other possible values between meaning after 1 0 0 1 like 1 0 1 0, 1 0 1 1, 1 1 1 1, those are not possible in binary coded decimal representation of a number, right. And therefore, if we are designing considering a combinational logic block which is receiving numbers in binary coded decimal format, then these numbers can never appear 1 0 1 0, 1 0 1 1 or 1 1 1 1. These cannot appear and therefore, these combination of values can be considered as do not care in the combinational logic block that is receiving binary coded decimal digits. Similarly, can also be those input combinations for which the output is not observed. In sometimes there can be cases in which for the input combinations for which output is never observed, right. Suppose there is an input combination which makes the output or the block which is observing the output go in a sleep state. Now, if the block is in the sleep state, whatever we produce the output, it will not be able to read it or it does not care to read it, right. And therefore, a function producing an output for a block that is in the sleep state, it can consider those inputs which is taking this the block at the output in the sleep state, those as a do not care conditions. Now, there can be a Boolean function which contains do not care. A Boolean function with do not care condition is there, then those Boolean functions are known as incompletely specified Boolean function. Now, how can we represent incompletely specified Boolean function? We can represent incompletely specified Boolean function using 3 sets. The first set is the on set. It contains input combinations for which the output is 1. The second set is the offset, meaning the input combinations for which the output is 0. And the third set is the do not care set or DC set, in which the input combinations, this is the input combinations for which the output is do not care or x, right. Let us take an example. Suppose there is a function of 3 variables x 1, x 2, x 3 and the value of this function takes 1 for these input combinations, right. So, we can say onset is equal to the input combination, set of input combination that produce 1, then offset is the set of input combinations which produces an output of 0, and do not care set are the set of input combination for which the function is a do not care, right. So, we can represent this function also in Hypercube, right. So, we say that for 0 1 0 and 0 1 1 we take write the output as 1, for 0 0 0 0 0 1 1 0 0 and 1 0 1 we write the output as 0, and for 1 1 0 and 1 1 1 we write as x, right. So, we can represent a incompletely, or we represent an incompletely Boolean specified Boolean function also as in a Hypercube representation. Now, let us understand a term which is known as implicant. What is an implicant of a Boolean function? Implicant of a Boolean function is a cube whose corners are all in the onset or do not care set, right. It can be either in the onset or in the do not care set, but it cannot be in the offset, right. So, what is an implicant? It is a cube, and what is a cube? Cube is a product of literals, right. So, implicant is a product of literals such that it covers, or whose corners are all only on the onset or do not care set. It should not go into the offset, right. So, let us take an example, right. So, suppose the Boolean function was this, or this is an incompletely specified Boolean function which was given. Now, in this case what can be the implicant? So, we can say that x1 bar, x2, x3, meaning that the combination is 0, we can write the combination as 0 and 1 and 0. For this 0 1 0, we see that 0 1 0 is this corner, right, and the value is 1, right. So, it is in the onset, and that is why this is an implicant. What about x1 x2? Now, x1 x2 means that x1 can take a value of 1, x2 can take a value of 1 and x3 can take any value, right. Now, what does it represent? It represent this corner 1 1 0 and 1 1 1, this corner, right, and both are do not care, right, and therefore, it is an implicant. Now, let us take the third example. The third example is x2 x3 bar. So, in this case x1 can take any value, I am specifying as dash, and then x2 can take a value of 1 and x3 can take a value of 0, right. So, 0 1 0 this one and 1 1 0 this two. So, it is 1 is in the onset, right, this one is in the onset and this one is in the do not care set, right. So, these two guys are there in x2 x3 dash, and they are either in the onset or in the do not care set, and therefore, x2 x3 dash is also an implicant. What about x2? If x2 is there, meaning that x1 can take any value, x2 can take 1 and x3 can again take any value, right. So, in that case these are the 4 corners, these are the 4 corners corresponding to x2, this one, this one, this one and this one. In these 4 corners x2 is taking a value of 1 and x1 and x3 can take any value, right. Now, all these are either in the onset or in the do not care set, and therefore, these are implicants. Now, let us take a few examples of a cube which are not implicant. For example, let us look into the cube x1 dash, meaning that x1 takes a value 0, x2 is not appearing. So, it can take any value, and x3 dash is taking a value, x3 is taking a value of 0, right. Now, 0, so this corner and this corner, right. So, this corner is okay, it is still in the on set, but this one is a 0 set, right, it is a 0 set, and therefore, it is intersecting with the offset, right, or and therefore, it is not an implicant, this is not an implicant. Now, what about x1 bar or x1 dash? So, it means that x1 can take a value of 0, x2 can take any value, x3 can take any value, right. So, it represent these corners, right, these corners. Right. So, all these corners x1 is 0 and x2 and x3 are varying, right. Now, again in this case these are in the offsets, these zeros are in offset, and therefore, this is not an implicant. Now, let us look into what is a cover of a Boolean function. Now, cover of a Boolean function is the set of implicants that includes all its minterms. For example, consider a function here, right. So, the minterms are these two are the minterms, right, where it is which corresponds to value 1 or the input combination or the corners at which the Boolean function takes a value of 1, those are basically the minterms of the function, right. So, in this case these are two minterms. Now, what is a cover? Cover is the set of implicants that includes all its minterms, meaning that this can be included, this can be included, right. Now, this is a set of implicants, right. So, by definition, as we discussed in the last slide, implicant will cover only the onset or do not care set, it cannot cover an offset, right. So, cover will only be covering the corners corresponding to do not care set and the onset, it cannot cover any corner corresponding to the offset, right, because it is cover is a set of implicants. So, what is a cover? Cover is the set of implicants that includes all its minterms, right. So, this so if we take a set as set of these two minterms or these two implicants x1 dash, x2, x3 dash and x1 dash, x2, x3, these two elements in the set, then it is covering both these ones and therefore, this is a cover. Now, let us take another example. Now, in if we consider this as 3 implicants, then these 3 set of implicants cover the cover both the ones. Of course, one is covering do not care, but that is okay, right. So, this is again a cover, the set of these three implicant is a cover. Let us take another example, right. Now, we take an implicant as x1 dash x2, right. x1 dash x2 means that x1 can take a value of 0, x2 can take a value of 1 and x3 can take any value, right. So, it corresponds to this corner and this corner, right. Now, this covers both the ones or both the minterms that were in the function, and therefore, x1 dash x2 is a cover of this function. Let us take another example, another implicant. So, another set of implicants. In this set there is only one element x2, right, only an element x2. It means that x1 can take any value, x2 will take a value of 1 and x3 can take again any value. So, it corresponds to these 4 vertices in the Boolean hyperspace, and therefore, since it covers these two ones and minterms, therefore, this implicant is also a cover, right. So, the number of implicants in a cover is known as the size of the cover. So, the size of this cover is 2, right, because there are 2 elements in this cover. In this the size is 3, right. In this the size is 1 because there is only one element in the cover, and in this the size is 1, right. Now, the cover with the minimum size is known as the minimum cover, right. So, in this case there are 2 covers with the same size, right. So, this and this both are the minimum cover, these 2 are the minimum covers. Now, let us look into another term which is known as prime implicant. Now, what is a prime implicant? Prime implicant is an implicant of a function that is not covered by any other implicant of that function, not covered by any other implicant of that function, right. It is, in short, we also call them as prime, right. So, now let us take an example. Suppose this is the function, Now, in this function, if we look into x2, right, the implicant x2. Now, x2 represents all these corners, right, all this x2 represent all these corners, and this implicant is not covered by any other implicant of this function, and therefore, this is a prime implicant, right. Now, if we look into say and another implicant x1 dash, meaning x1 is equal to 0, x2 is equal to 1 and x3 is equal to 0, right, 0 1 0, this corner, right. So, is it a prime implicant? No, it is not a prime implicant, because this implicant covers the other implicant also, right, and therefore, this is not a prime implicant. Now, what is a prime essential prime implicant? Now, if there is at least one min term that is covered by only that prime implicant, then that prime implicant is known as essential prime implicant. For example, consider this function which we had seen earlier. Now, in this case, there is if we consider x1 dash, then these three corners are covered, or this is not the min term, these two corners are covered only by x1 dash, and therefore, it is an essential prime implicant. And if we consider x2 dash x3, x2 dash x3 covers these two corners, right, and out of these two corners, this corner is covered only by x2 dash x3, and therefore, x2 dash x3 is also an essential prime. Now, let us take another example, right. In this case, there are 4 primes x1 dash x2 dash, this one, the another prime is this one, another is this one, and fourth one is this one, right. There are 4 primes in this case. Now, which of them are essential in this case? We can see that out of these four prime implicants, x1 dash x2 dash, right, this prime implicant is essential, because this corner is covered only by this prime implicant, right, and similarly this corner is covered only by the prime implicant x1 x2, and therefore, x1 dash x2 dash and x1 x2 are essential prime implicants. And the prime implicants x2 dash x3, that is this one, is not an essential prime implicant. Why? Because this corner is covered by x1 dash x2 dash, and this corner is also covered by x1 x3, right, and therefore, x2 x3 dash, that is this implicant is not a essential prime implicant. Similarly, x1 x3 is not a essential prime implicant, because each of these corners are covered by other prime implicants also. Now, let us look into, having looked into the definitions of various terminologies, now let us look into that what is logic or exact 2-level logic minimization. So, the aim of exact 2-level logic minimization is to find the minimum cover, right. So, we saw that what is minimum cover, right. So, we for a given Boolean function, we saw that there can be multiple covers, right, as in saw in the previous examples, there can be multiple covers, and different covers will have different sizes, and out of those covers, the cover which has got the minimum size, that is known as the minimum cover, and that the goal of exact 2-level logic minimization is to find that cover, the cover with the minimum size. Now, why do we want to find a cover of minimum size? Because it correlates well with the circuit area. If we minimize the size of a cover, we will typically be able to reduce the hardware cost or reduce the area of the circuit. Now, for simpler problems, you might have in your digital circuit course, you might have looked into various methods of minimizing a logic function, right. For example, you might have done minimization using Boolean algebra methods. You apply, for example, De Morgan's law and commutative associativity and other properties of Boolean Boolean operators, and based on that you could have done the minimization, or you might have used the Kerning maps to minimize the logic, right. Now, these techniques work when the number of variables are small, right, but when the number of variables increases, typically say more than 20 variables, then conventional techniques are not of much use, and in that case we need to use some systematic way to do logic minimization that we will be looking at, right. Now, to find the minimum cover, we reduce the search space, right. Now, out of all possible covers, there are many covers possible for a complicated Boolean function, maybe say if the Boolean function is having more than 20 variables or so. So, in that case we need to reduce the search space where to look at for the minimum cover, right. So, we reduce the space of exploration of minimum cover with the help of a theorem which is known as Quine's theorem. Okay. So, let us understand what the Quine's theorem is. So, to understand Quine's theorem, first let us define a term which is known as prime cover. So, what is a prime cover? Prime cover is a cover which is consisting only of prime implicants, right. It will contain not any other implicants, only the prime implicants, right. A cover which consists only of prime implicants, that is known as the prime cover. Now, what is Quine's theorem? Quine's theorem states that there exists a minimum cover which we are trying to find. There exists a minimum cover consisting only of prime implicants, or there exists a minimum cover which is a prime cover, right. Now, why it is true? What is the basis of Quine's theorem? We can make the following observation. Now, consider a minimum cover, assume that it is not a prime cover, right. Assume first that with the Quine's theorem it is against the Quine's theorem, or we are saying that there is a minimum cover, which is not a prime cover, assume that, right. Then it implies that it contains some implicant which is not a prime implicant, right. Since it is not a prime cover it consists only of prime implicants. Now, we are saying that there is a minimum cover which is not a prime cover, meaning that this minimum cover will have some implicant which is not a prime implicant, right. Now, if that is the case, then we can replace each non-prime implicant with a prime implicant, right. We can always do that. Why? Because prime implicant covers other implicants, right. So, if there was a non-prime implicant, then that non-prime implicant can also be covered by some prime implicant, otherwise that would have been a prime implicant itself, right. So, so we can replace each non-prime implicant in the minimum cover with a prime implicant that contains it, right. Now, we got a new cover that consists only of prime covers. Why? Because which only consists of primes. So, why it happened? Because we have replaced all the non-prime implicants with the prime implicants. Now, this minimum cover contains only the prime implicants, right. And what will be the size of this this cover? The size of this will be the same as the original size, right. The size was, now since we have replaced each of the non-prime implicant with a prime implicant, right. So, the size is not changing, right. But what we have done is that we made a non-prime cover to a prime cover, right. Hence, there exists a minimum cover that is a prime cover. So, what it means is that we derived another cover out of it that is now a prime cover. So, given a minimum cover, we can always come with a prime cover which is of the same size, or it will be better or smaller size than other covers which contains non-prime implicants, right. So, what is the application of this Quine's theorem? The application is that we can focus only on the prime cover, right, or we can only consider those covers which are consisting of prime implicants, right. So, we can focus only on those covers that consist of prime implicants, and therefore, our search space for finding the minimum cover, that has reduced substantially. We need not bother about the covers which are there, which are and consist of non-prime implicants. Now, how to find minimum cover among the prime covers? Now, we can do it by finding first the set of prime implicants for a given function, and then building a prime implicant table. Now, what is a prime implicant table? So, we can build a prime implicant table by arranging the prime implicants in separate columns, right. So, we have separate columns for different prime implicant 1, prime implicant 2 and prime implicant 3 and so on, and the minterms are in the individual rows. So, we arrange minterm 1, minterm 2 and so on in rows, and we make an entry in the table as 1 if the given prime implicant covers the given minterm. We make it as 1, otherwise make it at 0. So, let us take an example and understand. Suppose this was the given function, and in which we have 4 prime implicants. These are the 4 prime implicants, first one, second, third and fourth, right. 4 prime implicants are there, right, and how many minterms are there? 1, 2, 3, 4 and 5 minterms are there. So, we will build a table. First we arrange all the minterms in various rows, right. So, we have 5 rows for 5 minterms, right, and then we have the prime implicants arranged along the columns, right. So, there are 4 prime implicants. So, we have 4 columns here. Now, we make the entries of these of this table as 1 or 0. Now, where do we make the entry as 1? For example, x1 dash x2 dash is this prime implicant, and it covers the corner 0 0 1 and 0 0 0, and therefore 0 0 0 and 0 0 1, these 2 minterms are covered, and we make the entry as 1. For rest we make it as 0. Similarly, x2 dash x3 is this minterm, is this implicant, and it covers the corner 0 0 1, right, 0 0 1 and 1 0 1, right, 1 0 1, and therefore, we make these 2 entries as 1 and rest as 0, and similarly we make the entries of other entries in the table. Now, how to find minimum cover using prime implicant table? Now, we have built the prime implicant table. Now, how to minimize it? Now, how to get a minimum cover out of it? So, now finding the minimum set of columns that covers all the rows in the prime implicant table, that is the job that needs to be done, right. Now, we want to cover all the minterm, then only we get a cover, valid cover, right. So, we have to select minimum number of columns such that all the minterms get covered, right. So, this is the problem. Now, this problem is same as set covering problem, which is studied extensively in graph theory, and this is the same problem that we encounter here. So, this problem is known to be an NP complete problem or a difficult problem, right, and the complexity of this problem increases with the number of variables. Why? Because as we increase the number of variables, then the prime implicant can increase greatly or exponentially, and the number of minterms can also grow exponentially, right. So, the table size will become huge. So, if the table size becomes huge, then finding or finding a solution for set covering problem also becomes difficult, right. And therefore, this set covering problem is can be solved for simpler Boolean optimization problems, right. So, now this is a difficult problem and we can make some simplification or simplify the task for set covering problem. What we can do is that first notice that if there are some essential primes, those will always be there in the cover. Why it has to be there in the cover? Because there are some minterms which are covered by only these essential primes, right. So, in this case we had seen earlier that this prime and this prime, these two were essential primes. Why? Because this corner was covered only by x1 dash, x2 dash, and this corner was covered only by x1, x2, right. And therefore, these two primes will always be there in the cover, right. So, we identify these essential primes and then get rid of the rows which are already covered by this, right, by these two essential primes. So, in this case this is already covered, this is also covered, and if we select this prime also, then this is covered and this is also covered, right. Now, we need to work on the remaining min terms. So, in this case the remaining min terms is only 101, right. So, for 101 we can take either this or this, right, any of that will do. So, if we take the cover as this set, this and this, or we can take this, this and this, right. There are two possible minimum cover in this case, right. So, there I just gave one example of the reduction technique that is based on essential primes. There are other many efficient techniques which try to reduce the number of variables or reduce number of vertices that needs to be handled by the set covering problem. Okay. So, using with the help of those reduction techniques and some heuristics in the covering algorithm, this problem of exact logic minimization can be tackled efficiently. However, when the problem size becomes very large, right, in that case suppose say number of variables is more than 100 and the number of min terms is say more than 1000 or number of cubes that needs to be handled by or number of primes that needs to be handled by the minimizer is say more than thousands. In that case, we do not do exact logic minimization or we do not try to find the minimum cover. What we try to do is take help of heuristic minimizer. And what is heuristic minimizer? So, for large problems we prefer heuristic minimizer over exact minimization, and heuristic minimizers are faster for large problem sizes, and we often do not need the exact minimum cover, right. So, many a times what happens is that say suppose there is a cover which the exact theoretical minimum cover size is say 980, and if a heuristic minimizer which tries to find a minimal cover rather than a minimum cover, and the number of elements or in the number of cubes in the cover is or number of implicants in the cover is instead of 980 it is say 988, right. It is not exactly same as the minimum cover, but slightly more than that. It is still okay, right. So, there will be slightly a small area penalty or there will be some scope of logic minimization that is still left, but still it is okay, right. So, we often do not need exact minimum cover. Any solution that can be found quickly and is near optimal is acceptable, right. So, in this case rather than spending an hour, if we can find a approximate minimum cover. So, say instead of 980 implicant, we have say 988 implicant, right. Then also it is more, for most application it is acceptable, right. And that is why we go for heuristic minimizer, which are very fast compared to exact logic minimization, and they reach or they are able to do minimization fairly well, not exact logic minimization, but close to logic close to theoretical logic minimization. Now, the heuristic minimizer tries to find a minimal cover rather than the minimum cover. And what is a minimal cover? A minimal cover satisfies certain local minimum cover property rather than the global minimum property, right. And what an example of this local minimum cover property is that a cover in which no implicant is contained in any other implicant of the cover. So, we find a we find a cover in which one implicant does not exist any implicant which is covered by any other implicant, right. If there is such an implicant, we get rid of that implicant safely from the cover, and then the cover that we get, it is known as a cover which is minimal with respect to single implicant containment, right. So, minimal cover, so the heuristic minimizer tries to find a minimal cover which is minimal with respect to single implicant containment, meaning that no implicant is there in the cover which is covered by any other implicant of the cover. So, the size of the minimal cover can be more than the size of the minimum cover, but then we are fine with it, because if the minimal cover is still close to the minimum cover, we are fine with it. And for many applications or many practical cases, this heuristic minimizer is able to find a minimal cover which is close to the minimum cover. Now, what is the approach of the heuristic minimizer? It basically starts with an initial cover. It need not be a prime cover, it can be initial cover, and it iteratively improves the solution by applying some operators on it. So, we start with some cover which may not be a prime cover, and then we successively apply various operators on it, and we apply it such that we are not able to make any improvement. So, the iteration terminates when the algorithm can no longer improve the solution. And what are these operators? These operators are, for example, the expand operator. So, in expand operator, what is done is that it expands a non-prime implicant. So, we started with a cover which was not a prime cover. So, there will be some implicant which is not a prime implicant, right. So, what does expand do? It expands a non-prime implicant to make it prime, and as a result of it, it removes implicants covered by the expanded implicant. So, the expand operator will make a non-prime implicant as a prime, and it will remove the implicants which are already covered by other implicants or the expanded implicant. Then the other operator is the reduce operator. So, what it does? The reduce operator, it replaces an implicant with a reduced implicant, right. So, it will cover fewer min terms, right. So, it will cover fewer min terms. So, as the cover size will not change, right. The cover size will not change, and the function will still be covered. Why? Because it replaces an implicant with a reduced implicant such that the function is still covered. So, it is not removing any, or it is not reducing an implicant such that it makes a corner which was covered by it uncovered, right. So, it does not reduce the size of the implicant such that it removes or it uncovers a vertex which was solely covered by it, right. So, it means that if it is reducing from a vertex which was already covered by some other implicant also, right. So, we carry out this reduce of implicant the reduce operator, so that in successive operations a better solution can be achieved. Then there is an operator which is reshape. It operates on a pair of implicants. It expands one implicant and reduces the other such that the function is still covered. Note that the size of the cover remains the same. And next is the irredundant operation. It makes the cover irredundant. And what is an irredundant cover? It is a cover in which if we remove any implicant, then it will be no more a cover, meaning that if there is an implicant which covers the corners which is covered by a set of other implicants of the cover, then we say that that particular implicant is a redundant implicant and we can remove it, right. So, the irredundant cover removes an implicant or removes a redundant implicant, and after it has removed all the redundant implicants, the cover that we obtain is known as irredundant cover. And in an irredundant cover, there is, if we remove any of the implicant out of it, then some min term will be left uncovered, right, then it will no more be a cover. Now, let us take an example like how the heuristic minimizer works. Now, let us take this function in which we have say 1, 2, 3, 4, 5 min terms, right, and we start with a solution which is consisting of only the min terms, sum of min terms form. So, there are 1 implicant, 2, 3, 4, 5 implicants are there. Now, we apply the expand operator. So, this expanded in this expanded this expanded to this expanded to. So, after the expand operation and removing the implicant which gets covered by expansion, we get a cover in which instead of now earlier we had 1, 2, 3, 4, 5 implicants. Now, we have 1, 2, 3, 4 implicants, right. Now, from 5 we move to 4 after expansion. Now, after that we do a reduce, right, we reduce this particular implicant. So, it now covers only this min term, right, and others are unaffected. So, the size of the cover is still 4. Now, after reduce we do a reshape. What we do is that we expand this min term or this implicant and reduce this implicant, right, we reduce this and reduce this implicant. So, we still get after reshape the number of cubes or number of implicants that is in the cover size is not changing, it is still 4. So, we have one implicant another and this one got reduced to an implicant which covers only one min term and we have the fourth implicant, right. And then again we apply an expand operator, and once we apply the expand operator, then this implicant gets rid of, we get rid of this implicant and finally we have 3 implicants in the cover, or the cover size is 3, right. So, we started with 5, then we got to 4, then got to 4 and finally we reached to a cover size 3, right. Now, in this case there is no redundant implicant, right. If we remove any of these implicant, it will no more be a cover, right. But in typically what is done, that after we have carried out an iteration of expand, reduce, reshape, expand, reduce, reshape multiple times, at the end we again carry out an irredundant operation, so that if possible some implicant can be reduced, right. So, in this case it is not required to carry out an irredundant operation, or it will not yield any improvement. Now, in this case it turns out that we are getting a minimum cover also in this heuristic minimizer, but it is not that we will always be getting a minimum cover using this heuristic minimizer. Now, if you want to go deeper into these topics, this is a very good reference, okay, and you can also look into this reference. Now, to summarize, in this lecture what we have done is that we have looked into the logic optimization task, and in particular we looked into logic optimization or logic minimization of two-level combinational logic. So, in two-level combinational logic we looked into two types of minimization, one was exact minimization and the other was heuristic based, right. So, in the next lecture we will be looking into another logic optimization technique, that is multi-level logic optimization. Thank you very much.